Hello, my name is Aaron Groff, and I've been working with Dr. James Shogren-Harris in the Department of Chemical and Biological Engineering, and my project is the effects of various catalysts on the synthesis of ethyl acetate via ethanol oxidative self-coupling reactions. So to start, I wanted to discuss a little bit of the background of this project. N,4-hydroxyphenyl acetamide, also known as paracetamol or acetaminophen, is found in a lot of common over-the-counter medications, such as Tylenol and Sudafed, and these medications are used to treat pain. Paracetamol is commercially synthesized using the reaction scheme shown at the bottom, with acetic anhydride and 4-aminophenol using to form this molecule. However, we think there might be a better way to do this, and that is by utilizing the oxidative coupling of ethanol. In the reaction in yellow, you can see that ethanol, when reacted with oxygen, will form acetaldehyde with water as a byproduct. And then when reacted with ethanol again, will form ethyl acetate. We think that ethyl acetate could be a cheaper alternative to the acetic anhydride shown in the reaction scheme here. However, as you can see in the blue, there's a couple problems with this as far as there's a couple byproducts that we think might be formed instead. And we don't know if carbon-nitrogen or carbon-oxygen bond formation will be favored in this reaction. We want to determine whether the pH will influence the product selectivity as well as our choice of catalyst. Will that influence product selectivity? However, if we can synthesize paracetamol using this reaction, we think that ethanol could end up being a cheaper alternative to the acetic anhydride in synthesizing acetaminophen. So now to talk a little bit more about catalysts. Dr. Harris's lab focuses a lot about catalysts, how they're used, how they can benefit reactions, and how they differ from each other. So I want to talk to you a little bit about how catalysts work. Catalysts work by reducing the activation energy of a chemical reaction. This is going to help speed up the chemical reaction and end up producing more product. As you can see in the middle here, ethanol reacts with oxygen atoms that have adhered to the surface of the catalyst, represented by these blue circles, and then form acetaldehyde. When reacted with ethanol again, will form the ethyl acetate. And the main takeaway here is catalysts made by SEA, which stands for strong electrostatic adsorption, and it's the method that I synthesize my catalysts with. This is going to create metal nanoparticles that are small and well dispersed. This improves the catalytic activity of the sample and makes sure it's well dispersed across the entire sample. Also, transition metal catalysts are going to be able to selectively oxidize the ethanol to form acetaldehyde instead of complete combustion, which would result in carbon dioxide, which we don't want for both environmental reasons as well as it's just not a very valuable product. Now, I'd like to discuss how synthesizing one of these catalysts works. So I'm going to walk you through a synthesis of a ruthenium on titania catalyst by strong electrostatic adsorption. First, I create a mixture using the first ingredient being a ruthenium chloride salt. This is our source of ruthenium, the transition metal catalyst, really where the magic is happening in this reaction. You put that into an amount of water, which is the solvent for this reaction where everything is kind of taking place. It doesn't actually interact with the chemicals though. You also add ammonium hydroxide, and basically this is going to help the ruthenium adhere to the surface of the support. And what the support is for, this is the 1 gram of titania that is added. This is so that we can dilute the catalyst. Ruthenium is a very expensive metal, so we don't want to use all ruthenium. Instead, we want to dilute it with titania, but it's going to keep the same enhanced catalytic properties that ruthenium has as long as the ruthenium is spread out along the titania surface evenly, which is the goal of this SEA catalyst synthesis method. Next, we're going to stir our mixture and then check the pH. After we do that, we're going to adjust the pH by adding ammonium hydroxide, which will increase the pH of the mixture because it is a basic substance. And we want to get it to 10.5 because that's going to maximize the adsorption of our ruthenium onto the titania, which is what we want. Next, we're going to wash and cover our samples, and then we are going to vacuum dry them for 1 day. This is going to get them dry so that we can then reduce them in a tube furnace. This is done at elevated temperature, 400 degrees Celsius, flowing a partial hydrogen environment over it. And basically what this is doing is it's preparing our catalyst so that we can use it in our reactions. Next, we're going to crush and sieve the catalyst, and the idea here is to get particles that are all roughly the same size. We want as uniform as catalyst as possible because that's going to improve their catalytic activity and make them very consistent. I also did this synthesis with other metals such as rhodium, palladium, and platinum. All of these are transition metals, so we would expect them to behave relatively similarly. However, they're all different, so we want to check which one is going to behave the best for our reactions and which one is going to give us the best yield of our products. Now, I'd like to talk about some of the reactions that we plan to run using these catalysts. The first step was creating standards for GCMS analysis of ethyl acetate. And GCMS is basically just a machine that's going to allow us to analyze the product solution that we create and determine how much ethyl acetate has formed inside of it. Next, I created a few models, which I'm going to discuss in the following charts, which allowed me to reassess the reaction conditions given this information. So the first model that I made is boiling point of ethanol versus pressure. This is looking at, as you increase the pressure, how does the boiling point affect? And as you can see, as the pressure inside the reaction vessel increases, the boiling point of ethanol is also going to increase. And I'll discuss why this is relevant a little later. Additionally, I created an oxygen solubility in ethanol versus pressure graph. And again, as the pressure increases, you notice that more and more oxygen will be dissolved inside of the ethanol. Additionally, these three different lines represent three different temperature scales. So as you go up in temperature, there's also going to be more oxygen dissolved inside the ethanol as well. So both temperature and pressure are correlated positively with the amount of oxygen dissolved inside the ethanol. So why does this matter? From the data, it can be seen that the higher pressures are advantageous for this reaction. Reactions can be run at higher temperatures with ethanol still in the liquid form. And this is very important because higher temperatures are going to lead to more reaction, more product formation, because the reactants are going to have more energy due to that higher temperature. Now, higher temperatures would generally not be possible because ethanol has a relatively low boiling point, and we do not want the ethanol to boil. Once it turns into a vapor, you're not going to run the reaction inside of the liquid, and it also can be very dangerous. Vapors expand, and then you could get some sort of like rupture of the reaction vessel, and we definitely don't want that. So running at higher pressure allows the ethanol to stay in liquid form even at higher temperatures, which is going to be advantageous for a reaction. Additionally, more oxygen will be present in the reaction mixture and available to adsorb to the catalyst at higher pressure. Long story short, you want as much reactant as possible so you can form more product. And basically, pressure is going to help us do this because it's going to cause more oxygen to dissolve inside of our ethanol, and the more oxygen that's available, the more ethyl acetate that we can form. And then lastly, at higher temperatures, even more oxygen will be present in the mixture, which again is only made possible by the higher pressures preventing the ethanol from boiling. So we want to look to run these reactions with the maximum safe pressures that we can. As for future goals, I want to continue synthesizing more various metal catalysts on titania by SEA. I'm looking at potentially iridium as well, also gold, silver, and maybe nickel. And then also I want to continue with silica-supported metal catalysts. Silica is another support as opposed to titania, and that could also impact the catalytic properties. So we want to take a look at how that could possibly impact and see which catalyst is going to perform the best as far as making the most ethyl acetate. We also want to start ethanol self-coupling batch reactions, see the reactions that we're actually wanting to run, and then we want to run these at different lengths of time. This is going to allow us to analyze the product solutions, and because we have different times, calculate the reaction rate and determine how that reaction rate changes over time. The reaction rate is a very important metric as it's going to help us evaluate if this idea and this pathway to forming acetaminophen is actually feasible, number one, and number two, which catalyst is going to have the highest reaction rate and which catalyst is going to perform the best in these reactions. Here's a list of my references, and then thank you all very much for listening, and if you have any questions, I would be happy to answer them.
Why did you choose titania for your catalyst substrate?
So titania is a pretty common use for a support. Silica is another pretty common one. Those are just like typical ones that are going with as far as like in sort of catalysis. So they were pretty obvious choices in that way.
Have you begun comparing the effectiveness of the different catalysts, and if so, which ones have shown to be the most effective?
So we have not started comparing the effects of these catalysts because we haven't actually ran and analyzed the results from the reactions yet. That's kind of the next step. That's what we're working towards. But definitely that's going to be very important as we want to determine which catalyst is going to be the best. So that will be a huge part of our research going forward.
What's the monetary difference between the ethanol and the other version if these platinum group metals are so expensive?
Okay, that's a great point. So some of these metals that are used inside of this catalyst are very expensive, like you said. But the key point here is that catalysts are reusable. You don't have to have new catalyst every time you run this reaction because catalysts will regenerate themselves over the reaction period. So you will only need new ethanol and new oxygen, not new catalyst, which is why you may have more of an upfront cost, but over time, the ethanol being cheaper than, say, the acetic anhydride used currently is going to cause this to be more affordable over a longer period of time.